Alright, today's video I want to talk about kinetics, which is going to be chapter 20. When we're doing chemical reactions, we'd like to know two things. We'd like to know the driving force, which is delta G, and how fast the reaction is going to occur. How fast the reaction is going to occur is the topic of kinetics. This is just the speed of the reaction. And we're going to study kinetics in two ways. First, we're going to do an empirical analysis of the speed. Empirical analysis is by observation here. In other words, experimental measurements. In the second part of this chapter, we're going to look at the theoretical analysis of kinetics. And so, looking into the empirical end of things, we're going to figure out ways that we can monitor the progress of the reaction versus time. So typically what's plotted is something like concentration or amount. And so it could be the oxygen, how much oxygen is being produced, or it could be the hydrogen peroxide, how much hydrogen peroxide is being decomposed. And depends on which one's easier to analyze. It is possible to analyze the hydrogen peroxide concentration as a function of time here. And if we do that, we'll start off with a high concentration of hydrogen peroxide, but it will start to decline with time. And so when we analyze this here, we see that there's a trend here in which we're consuming hydrogen peroxide. However, 2 points are always going to define a straight line. If we have a curve, then we need at least 3 points here. You can see this third point, or even the fourth point, and the fifth point here. And so we might see some kind of trend like this, where it's not linear. We have more of a curve or non-linear behavior. And so this would be our empirical analysis here. And empirically, how does the hydrogen peroxide concentration change over time, like this? Okay, when we have a curve like this, it could also be linear. I mean, if the data fit it, a straight line like this. But this data here, clearly we see a non-linear fit. So analyzing curves like this, we look at the rate of reaction of hydrogen peroxide. The rate of reaction of hydrogen peroxide is equal to the delta hydrogen peroxide concentration over delta T. Delta hydrogen peroxide concentration is pretty much delta Y, over delta X. Delta Y over delta X is the slope of this. And so when we look at the slope, it's going to be the average rate over this time interval, delta T. It is let me pause this for a second. And then the average rate over delta T is just the average slope. Average slope. Let's try this again. Alright. The average slope over the time interval delta T, because what's happening here is the slope is continually changing here. It starts off at a very steep slope here, but then the slope gradually decreases here. And so by the time we get down here, the slope is quite a lot less steep. And so what that says is that the rate of reaction is changing over time, and it's non-linear. And so that's our observation there. So we have this, the average rate over time t, and we also have something called the instantaneous rate. The instantaneous rate at time t, and that is if you make delta very, very small, then we call it the d. So this is a infinitesimally small delta, or just a tiny, tiny delta. So we have d hydrogen peroxide over dt, and if that just becomes like a point of time, then what we'll have is something that looks like this. So here, I'll just blow this up where we can look at some data here. Let's just blow this up. So over this time interval here, what we have is the slope or the rate is continually changing like this, and we can draw different lines through this. So for example, the average rate over this time interval delta t, so delta t would be between the first and the third point here, and so this would be the average rate. The slope of this equals the average rate over this time interval from here to here. So this would be our delta t, delta time, which is delta x here, and this would be our delta y here, delta y. So that would be the average rate over this time interval delta t. However, we can have instantaneous rates, so for example, the instantaneous rate at this middle time here would be something like this, where the time interval becomes so small it just becomes a point on the line. And what we see is the instantaneous rate is the slope of the tangent line. And so slope of the tangent line at time t. So this is the second time interval here, and the slope of the tangent line here would be the instantaneous rate at that time. And then we could draw other tangent lines. So let's say the beginning point here, we'll have a slope of the tangent line. It's much steeper. That would be the slope or the rate at time 0, and then we could have something at time t1 or t2 like this. Those would be the slopes of the tangent line. Okay, the next thing we have is something called the initial rate. The initial rate is the instantaneous rate at time 0, but sometimes it's very difficult to draw a tangent line at time 0. So what we'll say is that the initial rate could be also approximately equal to the average rate over an initial time interval in which less than 5% reaction has occurred. So for example, if we started off with 1.0 molar and we end up at 0.95 molar, that's about 5% reaction there. And so we want to make sure that less than 5% reaction has occurred. And looking here, less than 5% reaction has indeed occurred. And so if we take the average, of the initial points here, it could be the first 2 points. That would be closer than the first and the third point here. And so the closer we are, that is, the closer we are to a delta t being a very tiny interval at time 0, then the more we are towards the tangent line here. And so here, this would be a more accurate initial rate than, let's say, the first and the third point. But it doesn't matter as long, for us, it's not going to matter as long as less than 5% reactions occurred. So in this case, less than 5% reactions occurred. We're just going to take the slope, the average slope, or the average rate. I need to intersect those. And so the average is the initial rate if less than 5% has occurred reaction. Okay, that's the initial rate. So we have different things. Now, we can relate the rates to other quantities in here. And so sometimes we have something called the rate of reaction. One thing is the rates of reaction are positive quantities. So we usually take the absolute values of these things. And so let's take a look here at see how long. Really, the rate of reaction of the hydrogen peroxide is being consumed. So you can see this is a negative slope here as we're losing hydrogen peroxide over time. As we're losing hydrogen peroxide over time, that should be a negative, a loss of hydrogen peroxide. But because we like to keep rates positive, all rates as positive. So for example, instead of saying I have a rate of minus $10 per minute, you might just say the rate is $10 per minute. And so that would be something of this sort here. And so the rate of reaction of hydrogen peroxide is just this. But when we relate this to other things, like for example, if we look at the rate of production of oxygen in this particular reaction, oxygen, that's going to be positive. And so we can relate these two. However, oxygen is produced at half the amount as hydrogen that's decomposed because of the stoichiometry of this. So it's half a mole of O2. And so what we could say is that the rate of reaction of O2, rate of production, let's say, of O2, oxygen, is going to equal 1/2 the rate of reaction of the hydrogen peroxide. Where the 1/2 comes from is, well, it's got to be produced at half the rate. According to the stoichiometry here, it's 1/2 mole of oxygen for every 1 mole. Or, so that would be 1/2 rate. Come on. That's not working. Okay, let me pause this. See if I can figure this out. Another way of thinking about this 1/2 is we can convert this into this. The rate of oxygen production is going to be delta of the O2 over delta T. And so what we can do is we can set that equal to, in this case, it's going to be 1/2 mole of O2 for every 1 mole of H2O2. This is the stoichiometric ratio from the balanced chemical equation. And so that's another way we can do that using dimensions. And so if that's the case, then the rate of hydrogen peroxide formation is equal to 2 times the rate of the oxygen production. It's going to be consumed twice as fast, and the oxygen reacts half as fast. And so these are relationships. So in general, when we're looking at a rate of reaction, and we want to relate this stoichiometrically to other things in the particular equation, this could go to GG, so HH, etc. We can have the rate of reaction is going to be normalized to based on these coefficients here. So it's going to be 1 over A, delta A, over delta t, etc. So we haven't normalized. I mean, this would equal 1 over b delta b over delta t. Since these are consumed, we have to do absolute value because those will come out negative. If it's being formed, like for example 1 over g delta g over delta t, that's fine. We don't need to change the sign because this is going to be positive anyway. And so this is analyzing the curve here. Another thing we could do with these curves is we could look for a particular pattern. There's a number of patterns that we see here. For example, patterns. This we call linear decay or zero order. Okay, it's just a straight line. And so linear or zero order. Consumption or decay. This is going to be concentration versus time. And then there are a couple of other patterns here. So for example, one pattern is that when we look at consuming half, like say this is 1/2 the initial here, then this time it takes is called t1/2. And so if we have, we'll call this 1 here, and then we're down to 1/2 here, and that's t1/2. We call that the half-life. So some of these curves will have a constant half-life. So each time you cut the residual in half, so we cut this in half here, like that, it's going to take an additional t1/2 worth of time. So we cut it in half again, and then it's going to take another t1/2's worth of time. Okay, when we see this kind of decay here, this is called first order. Okay, let me pause. I'm going to continue this in the next segment, so I'll pause this to keep the recordings compact.